My name is Giorgio Savastano. I will talk about real-time detection of tsunami from the Ionosphere. So this project was a collaboration between University of Rome La Sapienza and JPL. We also collaborate with people from NOAA. So the outline of this presentation, the first part I will introduce our algorithm to estimate the TEC in real time. Then I will show you two study cases, the Hidagi 2012 and the Meteor tsunami event in 2013. I will show you a real-time simulation, our new real-time prototype, including multi-constellations and geostationary satellites. And lastly, I will talk about some conclusion, future perspectives. So Varian, the Varian algorithm, some of you may be already familiar, was designed in 2015, University of Rome La Sapienza, and then was further validated in 2016 at Jet Propulsion Laboratory. The methodology, we use dual frequency phase observation in order to remove all the non-dispersive effect. And then we do a time difference, a difference in time in order to remove the phase ambiguity and the interfrequency biases. The last step, we remove the psychoslip with some outlier strategy. And the last step, we integrate this value over time. So just a few equations. We start from the carrier phase observation. Then we apply a geometry combination, so L1 minus L2 for GPS, E1 minus E5A for Galileo, and so on for all the constellations. Then we do a time single difference in time, and we obtain the TEC perturbation between two consecutive epochs. Since the IPP, as you've seen from the previous presentation, is moving over time, this quantity that we estimate is equivalent to a total derivative of TEC. So there is a variation due to the temporal variation. And there is also the second terms due to the spatial gradient and the fact that the IPP is moving so as a certain velocity. The last step, we integrate this quantity, and we obtain this time series that we use to detect fast changes in the ionosphere. So the first event was the 2012 earthquake from our 2017 paper. It was a 7.8 earthquake, and the tsunami took more than 5 hours to reach the Hawaii island. So we used a very dense network of stations in Hawaii, 52 stations, and we processed this data in a real-time scenario, in a simulated real-time scenario, so using all information available in real time. And in this plot, I'm showing two satellites for a particular station for 5 days before and 5 days after the event. So the solid line represents the gravity waves detected from the ionosphere. These time series are not yet integrated and filtered. Here is our final product. So in this map, you can see the IPP trajectory from 7 satellites in view from 56 stations in the main island. The change in color represents the change in the TEC, and you can see that there is also a dependency on the direction where these IPP are moving. So the tsunamis arrive from northeast, and we have also some phase shift due to the direction of the movement of this IPP. So it's not enough to detect these gravity waves from the ionosphere. We need to estimate the propagation velocity and the direction of propagation in order to be sure that this perturbation is due to the oncoming tsunami wave. In order to do this, we use this plot when on the x-axis we have the time, And on the y-axis, we have the distance from the epicenter. These are the 5 satellites. And the black vertical line represents the time when the tsunami arrived to the Hawaii Islands. And the change in color, again, represents the change in the TC. And by interpolating the arrival time at different location, the slope of this line represents the horizontal propagation of this TID, assuming constant propagation. Okay, unfortunately, this movie is not working, but I will show you this animation manually. Okay. So on the background, we have the NOAA model, the MOS model. Plot on top of this model, we have this cluster of points, which represent the IPP moving from this station, the black dot in the main island. So you can see the change in color when the tsunami is passing nearby this cluster of points. You have change here, and from blue to red, since they are sensing this gravity wave coming from generated by the tsunami. This result was published for our 2017 paper. Now we move to the second event. It is a meteor tsunami event. So first of all, what is a meteor tsunami? I had another animation. So it's basically a tsunami generated by, not by an earthquake, but by a weather system. This radar animation shows the reflectivity, the moisture of the atmosphere. So we have this big mesoscale convective system. So this is a pressure anomaly, this low pressure anomaly, which is moving across the US when it's passing, arriving into the ocean due to inverted barometric effect and resonances due to the velocity of this wave weather system, generate this wave, this tsunami-like wave. So not all the weather system generate tsunamis, but the main factor is the speed of this perturbation. If the speed of the perturbation is equal to the wave speed on that region, we have pro-domain resonances, and this wave is amplified and can reach several centimeters. So in this case, we have this from the atmosphere. It is a big weather system, and what happened from the ocean. So we have another animation here. I will show you in a bit. So we have that this tsunami wave is driven by this weather system was moving away from the coast. But since here there is an Atlantic shelf break, so we have a very fast decrease on the bathymetry. This wave was reflected back towards the east coast of US. I'm going to show you the output from the PTWC Rift model from NOAA. And this is the output from this model, and you can see that this wave is reflected back when reach the continental shelf break, and will eventually reach the coast of US. So we extracted from this 2D model a point located here, and this is the time series that we see. So the first wave coming driven by the weather system, then the wave is reflected. So we see this reflected wave and amplified in amplitude. This is the wavelet analysis. So this is the content in frequency of this perturbation. So now we are interested to see the response of the ionosphere. We saw the atmosphere, we saw the ocean. how does the ionosphere respond to this perturbation. This is a GPS satellite, G16, from 2 stations, and again we have a wavelet analysis, and we have a bulk of frequency that is in the gravity wave regime. This is a GLONASS satellite. At the time there were also from this station available GLONASS satellites, and then we see the same kind of perturbation from 2 different stations. Now we can generate the same plot we saw for AIDA-GY. In this case, a little bit more challenging since we don't have a point as an epicenter point, so we have to compute this distance from a point in the coast, and in order to find patterns that are some coherent signal in the ionosphere. This is the day of the event. This is the day before, where we don't see much a signal except for some noise due to lower elevation angle. This is some preliminary result. Now putting all together, so the IPP and the model from the ocean, unfortunately for this, in the east coast of US, we don't have much dense array as we have in the west coast of US, but we can still see when the tsunami arrived to the coast, we see it is a TEC perturbation moving along this east coast, and then disappearing after the tsunami wave is gone. So this was the second study case we're working on, and now we'll show you a real-time simulation test. So going back to the AIDA-GY test, we applied this the same algorithm in a real-time way, so in a real-time stream of data. I have to go back here. So, and in this case, we also implemented the detection strategy. So the 2 horizontal green line are the 5 sigma level of confidence computed on the first half part of the time series. And the idea is when a gravity wave exceeds this value from negative to positive, we have the arrival time at that specific location. So here you can see the moment when, from that particular station, we were able to basically detect this arrival time at that particular location. Then using an array of stations and with the kind of technique I showed you before, we can understand if this wave is propagating in such a way that is due to a tsunami. With the next slide, I want to show you our new effort in collaboration with the GD GPS group at JPL, where we are actually processing real time 56 stations focusing on the Pacific area. We are processing 4 constellations: GPS, GLONASS, Galileo, and Beidou. And so we are now on the stage 1 when we are able to obtain this TEC time series in real time. We don't have yet the capability of detecting tsunami. This will be stage 2, detecting the arrival time at different locations, try to estimate the propagation properties of this wave. So this is the website. It's already online. And as you can see, we have different colors for different constellations. We have blue, which is GPS, red is GLONASS, and green Galileo, and we have magenta with Beidou. And so these are the IPP tracks computed in real time. And I would like to focus to show you an interesting plot here. You see, you have mainly tracks, but there are also some points. Some points are geostationary satellites. As you know, Beidou has 5 geostationary satellites, and this means that the IPP point is not moving, is fixed. Why is that so important? Because as we saw from the previous equation, we have part of the perturbation which is due to the fact that the IPP is moving. And so we have these time series that are less noisy, and they are continuous. We don't have arc, but we have continuous time series in time. I want to show you one of these time series. For some reason it's not. Okay, it may take a while for. But we also have information in real time of the last earthquake happened from USGS. So we can click here and see if there is some earthquake happening in some region that may trigger some tsunami wave. Okay, seems that this is not properly working. Or maybe a browser. Okay, so the website is online. You can go and play with it and check the different time series. But the point I want to make here is about the geostationary satellites. And we are now planning also to include SBAS constellation, so geostationary from GPS and mainly GPS because we are interested in this specific area. So what are the conclusion and the future perspectives? So right now our real-time capability is to estimate TEC time series in real time. We can define a threshold, an exceeding threshold that we will use to detect the gravity waves. We have the location of the IPP in real time using broadcast ephemeris. So when there is a big earthquake, we know the epicenter within a few minutes, and we compute the distance. So generate the time versus distance plot. And we are actually now processing several constellations. So we have a better coverage of the sky with different constellations at the same time. So the goals will be to move from this step 1 to step 2. So now use this real-time capability to actually detect possible tsunamis. So using this time series to using a threshold and detecting the arrival time at different locations. We also want to increase the coverage of this GNSS station, and in order to also generate some risk assessment map that can be used for tsunami early warning systems. Here I just wanted to thank the GDGPS group providing this amazing real-time system, and some of the people they help in this project. Thank you. Are there any questions?
I think this is probably a naive question, but I'm interested in, after thinking about the first talk, when you're talking about thunderstorms and other sources of ionospheric disturbances, how do you sort of separate those out from your tsunami detections?
Yes, so the ionosphere in the ionosphere, we have all sorts of interaction with the solid Earth, with the ocean, with the troposphere, with the way we are able to separate this event is basically by fixing the geometry. So in the case of earthquakes, we know the epicenter within 5 minutes. So we can compute the distance from the epicenter, and we can estimate the propagation of this wave. We know what kind of velocity we expect, since our wave driven by the tsunami. We know what velocity the tsunami is moving because it's mainly driven by the bathymetry. So we expect more or less the same horizontal velocity for this gravity, for this TID. So the way is to estimate the propagation and the direction of the propagation of these waves.
So that works for earthquakes, but not the meteor tsunamis?
For meteor tsunami, we are now trying to find a similar way to do the same approach. So it's more challenging since we don't have a point from which computed this distance. So we are still working on how to apply the same kind of approach for different driver, like could be like meteor tsunami in this case. Okay. Any other question? Okay, thank you very much.